Here's to demonstrate the filtering of the input button on both edges, on the rising edge as well as the falling edge. And we're going to use this for the input button, and the counter right now is 0. Every time that we push it down, the counter will count up. But the pushing of the button has the fluctuation effects of sending 1, maybe bounce back to 0 over, and then come to 1 again several times, and then finally stabilize at 1. So we're going to take the LEDs here as the indication that on the left side the input has come and being held. We call this hold LED. And then the left side of that is the filtered. The hold must have a signal that sustains amount of time, a period of time, a set period of time to give out to the filter. So then filter is the one that upon the rising edge will drive this counter that show us as number 0, 1, 2 and so forth. So we push this down here, the input button push down, and then you concentrate on this LED effects and the counter change. We push it down. Okay. And what happened is that the right side, the hold, respond to that and then get a value 1 in, and it's inverse logic, so it went off. And for 1 second, since it detects that there's no more change, and after 1 second it's long enough to determine that the filter can also have the value on the left side, so that is also off as 1. And then that rising edge 1 from the filtered is going to up count the counter. And the falling edge goes the same if I release this one. The hold first and then filter. And the counter remains because it doesn't operate on the falling edge. But when rising edge occurs again, I'm going to push this in. The hold and then filter, and the counter becomes 2 according to the filter. And then release. Okay. So the delay is actually to check if the input sustains. Then of course this is exaggerated delay. It's just for us visually to observe. And the real delay is set much faster. It can be a few milliseconds. So both edges are being done in this example. This is because whenever the button provides raw input, the mechanical switches, and that is not really perfect. It will bounce a few times, and then when it comes down it will bounce a few times. Now if I don't provide 1 second sustained period for the input, for the signal 1, I can hold it, release it, hold it, release it. You see the flickering of the hold LED. It gets 1 and then becomes 0, it gets 1, becomes 0. But it doesn't change the filter side, the left side, unless the holding is within at least 1 second. Then the filter side becomes 0, becomes 1 as well. When I release it, it's the same. If I release it and then hold it down, release, hold it down. So like the 1 from the input button is still there with the flickering of zeros, and the input button occasionally becomes 0. But that occasions are not long enough to be 1 second. That's the set time to recognize the signal is indeed 0. The previous video, which only detects the rising edge, because we were only interested in the rising edge, and it was easier to demonstrate that way. And here both edges are to be concerned. Therefore the hold and filter, these 2 registers, initially they are unknown. They are defined unknown. And upon the first master clock cycle, the real CLK, the raw input is not equals to unknown. If that is the case, Of course, the input button can also produce unknown pattern if the mechanical button is flaky, but usually it's not. So if nobody touches the button and the buttons are not pressed, the first master clock cycle in the system will show that the input is 0, and then the hold will be differentiated with it. It's different, and the hold will get 0, and then the whole time count will reset. And then this is driven by master clock. This always begin end. We're going to up count upon the rising edge of the master clock. And then the whole time counter will count up. We set the value here, which is really big, to give us 1 second counting time. That's the whole time. And then the filter will get hold. Filtered will get hold. That is the filtered signal. This is to say that hold signal must sustain 1 second without being changed by n, comparing to n, that is. So we are saying that the n is not changing for 1 second. Then what's being withheld is the filtered good input signal. So why 1 second, you say? Because the 32 MHz master clock produces 0.03 microsecond cycles, and from 0 to 0.25 ones is 32 meg counting, and that 32 meg times 0.03 microsecond is about 1 second period. So this gave us the enough time to look at the display of the LED diodes. Of course, this in reality we don't need to set in the normal operation this long, but probably like 15 bits. That's about 1 millisecond. And the filter is the one that drives the count line. We can say at pass edge of filter the signal from 0 to 1, and that is the time we count up the count line, and then count line is mapped to the bitmap for displaying the decimal digits from 0 through 9 as we know it. Okay, so this is going to have both edges from the input 0 to 1, 1 to 0 being checked to sustain a set amount of time before it's handled to filter, and then the operation is on the filtered signal, either pass edge or